So welcome to this symposium. This is the symposium for the finalist presentation of the Strazzabosco 2021 awards. Before to start, I would like to say a few words about ISSNAF. ISSNAF is the Italian Scientists and Scholars in North America Foundation. It's a non-profit organization whose mission is to connect, empower, and celebrate the Italian research community in North America. Thanks to the generosity of our sponsors, ISSNAF confers the Young Investigator Awards every year to outstanding early career Italian researchers working in North America. 3 finalists are selected from the pool of applicants through a peer review process. At this symposium, they will present the research accomplishments to the jury and to the general public as part of the evaluation process. Based on the presentations together with the application materials, the jury will decide the winner, select the winner among the 3 finalists. In particular, we are here for the Franco Strazzabosco Award for Research in Engineering 2021. The sponsor is the Strazzabosco family. The award was established in 2013 in memory of Dr. Engineer Franco Strazzabosco. And this award is a tribute to the entrepreneurial courage of Italian engineers who strive to apply scientific discoveries to the public advantage. The jury of this year, Strazzabosco Award, is composed as follows. Myself, I have the honor to be the award chair. I'm also a member of the ISSNAF Board of Directors. Dr. Elena Orlando, she is an assistant professor at the University of Trieste, Italy. She's also a senior scientist at Stanford University. And also Dr. Orlando is a member of the ISSNAF Board of Directors. The third jury is Professor Guglielmo Scovazzi of Duke University. The 3 finalists of the 2021 Strazzabosco Award are in alphabetical order: Dr. Francesco Monticone, Dr. Federico Rossi, and Dr. Bartolomeo Stellato. In a few seconds, we are going to start with the first presentation. And first, I would like to say a few words about the format. Each presenter will present for 15 minutes, and then there will be about 8 minutes for questions. Questions from the general public are welcome, as well as, of course, questions from the jury. So we'll start with the first presentation. It is by Professor Francesco Monticone. He is an assistant professor at Cornell University and is presenting on non-reciprocal photonics, creating one-way lanes for light. Please, Professor Monticone.
Can you hear me? Yes.
Yes.
All right. So thank you very much, Marcello, for the nice introduction. And it's a pleasure to give this talk at this symposium. Now, as you see, I slightly modified the title of the presentation to make it broader, because I will be talking about a broad range of topics that I've been working on recently that I think are of broad interest to the general audience and to the panelists here. So I'm an assistant professor of electrical and computer engineering at Cornell University, and my group works in general in different areas of applied electromagnetics, photonics, and optics. And do you see my screen right? Yes. Okay. And in particular, my group at Cornell seeks to better understand the fundamental and practical limits of light manipulation and approach or bypass these limits using new concepts, new designs, and especially new engineered metamaterials. So what are these metamaterials? These are artificial materials that have properties that not only depend on the chemistry of the material, so not just on the material composition, the atoms and molecules, but they also depend on the interaction of light, of the electromagnetic fields with subwavelength engineered inclusions which act as meta-atoms and meta-molecules. And over the past 20 years, there's been a lot of work in this area. Many people have designed different three-dimensional and two-dimensional metamaterials and metasurfaces with a lot of interesting properties. In particular, using metamaterials and some related concepts I will be talking about, it's possible to overcome some of the main limits of conventional electromagnetics, optics, and photonics. For example, the diffraction limit, which is a very important limit on the resolution of imaging system using conventional lenses, but also limits to absorption, scattering, energy harvesting, which are very relevant for very important technologies like photovoltaics and in general energy harvesting, and also limits related to symmetries that we may want to break. And I'll be talking about this in this presentation, for example, time reversal symmetry and reciprocity, and many other conventional limitations that we may want to overcome with these new designs and artificial materials. And in this presentation, I will briefly discuss some of the work done in my group to use these artificial materials and some related ideas to control light scattering, light focusing, light guiding, and light emission with a lot of flexibility for different applications. So let's start from the topic of light scattering. One of the most interesting ideas that came out of the field of metamaterials was the idea of using these artificial materials to design invisibility cloaks, to design something that is able to bend light around an object, and in that way you suppress the scattering, so the light scattered by the object, and the object looks invisible. So many interesting techniques have been proposed to achieve invisibility, and as I said, in more technical terms, this means suppressing the total scattering cross-section of an object. So they work very well. However, they typically work over a very narrow bandwidth, meaning for a single color or a narrow range of colors. So one relevant question that we asked ourselves is whether it's possible to design broadband invisibility devices, and for example, covering the entire visible range. Now, unfortunately, we found that there are some fundamental limits to the process of making an object invisible. So we found that there is a fundamental trade-off between how much you can reduce the scattering cross-section of an object and the bandwidth, so the range of colors over which you can do that. And that applies to any invisibility device that people have designed in the past 20 years or so. We also designed some of the best invisibility cloaks that you can think of, going as close as possible to this fundamental bound. However, it's clear from these fundamental limits that we derived that making a human scale object invisible is basically impossible. So we proved that it's possible perhaps to make an object of this scale invisible, but only for a single color. So invisibility devices don't have much potential for objects larger than several wavelengths. However, they work very well for small objects. So we tried to find some interesting application of this idea of invisibility, and we studied a nice application in a completely different context. That is in the context of near-field scanning optical microscopy. Now, this is a very mature technology to do microscopy in which you have a tiny probe which is used to capture subwavelength details from an illuminated sample. It works pretty well. As I said, it's a mature technology. However, the main problem is that the probe is not invisible. The probe scatters light, and that scattering will determine some artifacts. Okay, so for example, if that's the field distribution you are trying to measure, if it is a very intense resonant field distribution, when you bring this probe nearby, you have a lot of scattering back on the sample. And that scattered light will completely disrupt the field distribution you are trying to measure. So you end up measuring something different from what you are trying actually to measure. You measure also all of these artifacts. So taking inspiration from invisibility cloaks, we designed a modified probe in which we pattern the surface to essentially suppress the scattering from that probe, taking inspiration from metamaterial invisibility devices. And we managed to design a probe that is invisible, so when you use it to measure, it doesn't scatter much back on the sample, so you can measure much more accurately. And we also fabricated these modified probes, and we used it to measure a field distribution. And as you can see here on the left, if you use a conventional probe, you have a minimum of intensity in your measurements when you expect a maximum of intensity at the center of this field distribution. Instead, using the invisible probe that we designed, we can get a much better image. We recover the original field distribution, and we are able to measure that. So that's quite exciting. It's a strategy that could lead to very accurate, minimally perturbative, super resolution near field imaging. So that's a quite exciting possible technology inspired by invisibility devices. Now, another interesting topic I've been working on is the idea of using metamaterials and metasurfaces to, in general, miniaturize optical components for focusing and again for imaging applications. So the general vision of the field of metasurfaces, which is the two-dimensional version of metamaterials, is the idea of replacing and miniaturizing bulky optical components, for example, a conventional lens, into a much more compact device, just like a little membrane, very thin, that is able to do the same job of a lens, but over a very small thickness. So compressing a lens or a more complex optical system into a single little membrane. Or you could do much more. You could really control all degrees of freedom of the incident light and manipulating light with a lot of flexibility. And that's a very hot topic right now. There are many companies, startup companies, that have been founded to commercialize metasurfaces for to realize flat lenses and things like that. And this topic has attracted attention from the international news outlets like BBC News and the New York Times. It's a very hot topic. And over the years, my group has designed the different metasurfaces to realize, for example, beam deflection, negative refraction, focusing, or more complex wavefront transformations. So with this planar structure, with a lot of little meta atoms interacting with light, we can really control the transmitted wave with a lot of flexibility. And then we fabricated some of these devices for operation at microwaves to design better antenna systems and also at visible wavelengths. So all of this is great. However, miniaturizing lenses is not enough if you want to, compress a very complex optical system like this super achromat telephoto lens that I'm showing here. So if you want to miniaturize this entire system, you also have to find a way to miniaturize the free space regions between lenses. Okay, so to do that, we have to invent a new optical component that some of our collaborators called a space plate that essentially mimics the response of free space and compresses free space from an optical point of view, compresses free space into a much smaller thickness. So we designed one of the best possible space plates recently, and that's how it works. So imagine now we have a flat lens focusing light at a certain distance. So here I'm plotting the field distribution, the field intensity. So you are focusing at this distance, right? Then if you insert one of these space plates, you would be able to move the focal plane closer and closer to your device, all the way to the back face of this single device here. So that's quite exciting because you can move the focal plane much closer to your lens, but the focal spot, the size of the focal spot, so the resolution and other imaging metrics are the same as before. So you can do the same imaging functionality, for example, magnification, but with a drastically shorter propagation length. So it's very interesting. We are very excited about this idea to potentially realize ultra-compact, planar, fully solid-state imaging systems in which an entire optical system, including lenses, free space, and everything, is compressed into a single device that you can then integrate right on top of the detector. So in the long-term vision of this idea, we would be able to create paper-thin cameras, paper-thin microscopes, paper-thin telescopes. That's quite exciting, and we are currently working on the design and fabrication of some of these devices for different applications. All right, now for the last few minutes of this presentation, I also would like to talk about our work on modifying another very important property and functionality of optical system, which is modifying how light is guided in a waveguide or optical fiber, right? So many of you are familiar with different systems to guide light. As I said, the most common is the optical fiber, but all of these systems, optical fibers, waveguides, of any kind, they have a very common, very important symmetry, which is known as time reversal symmetry or reciprocity, which means that you are able to transmit in one direction equally well as in the opposite direction. Now that's great for many applications. However, for other applications, we may want to break this symmetry. We may want to have unidirectional waveguiding. Why do we want to have that? We may want to have that property because in that way, the wave will not be able to scatter back, to reflect back. So we would be able to guide light around a band or discontinuity without any reflection. So in that way, we don't lose any energy in the reflection. Now, usually to do this, it's very complicated. We would have to use some special materials with an applied magnetic field. So that's called Faraday's effect. And it's something we can do, but it's complicated. And you have to use bulky systems and very expensive systems. But recently we studied a different strategy to break time reversal symmetry and reciprocity. And this is how it works. So imagine you have a little dipole source, for example, an antenna above a substrate. Now that's the field distribution you get, okay? You get a wave that propagates reciprocally and omnidirectionally. Just like throwing a rock in a pond, you have this wave propagating cylindrically on that plane, right? But now, if you apply a current to the substrate and the current is sufficiently strong, what may happen is that the movement of free electrons in the current may produce a Doppler shift. So essentially, by driving a current, you are mimicking a moving medium here. So you get this Doppler shift, so the optical properties now become direction dependent, and that's the field distribution that you get. You get the wave propagating only toward left. Actually, the wave is prohibited from propagating toward right. It cannot go in that direction. And as I said, if we have something like this, then you can design systems in which you are able to reroute a wave around a complex object without any scattering, any reflections. So that's quite exciting to be able to, reroute waves without losing any energy in reflections. But there are many other opportunities of systems with broken time reversal symmetry. For example, we studied the idea of launching a one-way wave against a termination. And in this case, you can get very high field hotspots at the termination, and you can use that to boost light matter interactions at that point with very high field intensity. Or you could break symmetries between light emission and absorption. For example, designing a system that absorbs very well in one direction, and at the same time, it doesn't emit light and radiation in the same direction. So you're not losing energy in that direction. And in this way, we could design better photovoltaic systems and in general, better energy harvesting systems. Now, the last thing I want to say is also related to the topic of light emission, but in a much more general context. So as probably many of you know, anything, pretty much anything with a non-zero temperature emits thermal radiation. For example, infrared light. And that's how thermal cameras work, right? You see infrared light due to the non-zero temperature of that object. So the object is actually losing energy through thermal radiation. So the question that we can ask is, can this emission process be used efficiently to cool down objects passively and efficiently by losing energy through radiation? And indeed, yes, our entire planet, if you think about it, cools down through thermal radiation every day. That's how our planet keeps a relatively constant temperature, by absorbing solar radiation and then re-emitting some radiation out in outer space, right? And in this way, the planet is able to cool itself down, right? And it's able to do that because the atmosphere is actually transparent in the infrared range of the electromagnetic spectrum. The atmosphere has different transparency windows for photons. So it allows photons from the sun to enter, and it allows photons at infrared wavelengths to escape. So if we want to maximize the cooling power that we get from an object, what we should do would be to minimize the energy absorption from sunlight and maximize the energy lost through thermal radiation. And that's exactly what we have done recently together with a startup company in Ithaca, for which I'm serving as Chief Science Officer. We designed scalable thin films for high efficiency passive radiative cooling. So these thin films are very simple, just polymers with some embedded microscatterers, and they are basically transparent in the visible range, so they don't absorb much sunlight, but they are designed to have a very specific emissivity spectrum with maximum emissivity aligned with the atmospheric transparency windows in the infrared. And in this way, we can really cool down an object efficiently, and we measured that we can get a greater than 50 watts per meter squared daytime cooling power. So this thing sitting under sunlight is able to cool down through radiative emission very efficiently. All right, so I think my time is up. So I hope this presentation has gave you a good idea of my different areas of work and these different new opportunities for light manipulation using metamaterials, nanostructures, non-reciprocal materials, and that's all I got. I thank you for your attention. I would like to thank also my students, postdocs, and funding agencies, and I'd be happy to take any question that you might have. Thanks.
Thank you, Professor Monticone. We have time for a few questions. I will start with the jury questions, if there is any.
I just want to congratulate you for this very interesting presentation. I learned a little bit about metamaterial, but I actually did my PhD at Stanford, so I was a student of Boyd as a master's student in one of the courses. I didn't do a PhD with him. I just took a course from him. So I resonate what you guys are saying about him. I think that you made pretty clear that what are your contribution and the innovation. So we can take that everything that you mentioned is basically the outcomes of your research. You define pretty well what is basically prior work and what is your work. Mm-hmm. So I don't have a particular questions. I mean, I'm not an expert in metamaterials per se, but I see that as we had this massive wave of nanomaterials a few years ago in terms of research, and I think the metamaterials are quite interesting because they're manufacturable. You can actually basically see them in action instead of theorizing them and then being challenged to actually realize them in a practical.
I agree, especially the metasurfaces I was talking about, because these are two-dimensional structures. So they are relatively easy to fabricate. Three-dimensional metamaterials are, of course, much more complicated to fabricate, but flat lenses based on metamaterials, this is something that people are commercializing right now. And for example, Facebook is actually reaching out to my group to hire students who are experts in designing flat lenses because they are interested in, for example, creating flat optical systems
Oculus.
or augmented reality.
I do some consulting with Oculus in the past, so I understand why they would need it. Yeah. Sorry, I don't want to steal additional questions from the audience.
I think we have time for a very short question, if anybody has.
So I have a question. Actually, thank you very much. A very interesting presentation. And so with your method, actually, are you going to solve the limitation, to tackle the limitation on the colors that you referred at the beginning of your presentation, that it works just with one color?
Yeah, that's a great question. So on the one hand, we found the fundamental limit. So we said, okay, there is no hope to make, invisibility cloaks for very big objects. So that's why we looked into other applications. For example, making these nanoprobes invisible so we can measure better. However, these fundamental limitations do have some assumptions. So there is probably one strategy that we are investigating now to maybe go beyond these limitations, which is passivity. So those bounds, those fundamental limits are based on causality of the scattering process and the passivity of the scattering process. Now, causality we cannot break because it's a fundamental property of nature. Passivity we could break. Maybe if we have an active system, and we have a paper now on that, active meaning you have gain media or some amplifying process. Now, maybe in that way, we can break some of these limitations. Actually, we proved that we can break the limitation. However, there are other problems then. There are other problems that if you have an amplifying process, you may get instabilities in the system. So your system may start, actually, it may start lasing. So it goes from being an invisibility cloak to a laser. It's quite interesting. So there is one assumption we can break, which is passivity, but by breaking that, we end up with many other problems. So we don't know yet how much we can push that idea. So, but that's a great question. Yeah.
Thank you. And for the sake of time, we need to stop here, but thank you very much for this very interesting presentation. And
thank you, everyone.
Congratulations on your achievement. So our second presenter will be Dr. Federico Rossi. He is a robotics technologist at the Jet Propulsion Laboratory, California Institute of Technology, and is presenting about algorithms that make teams of autonomous robots work effectively together. Please, Dr. Rossi.
Thank you very much. Thank you for the introduction, and thank you all for being here. Thanks for having me. It's a true honor presenting here today. I'm Federico from JPL, and I want to tell you about my work on how to make multiple robots play well together. So, why are we interested in this problem? Why is JPL and NASA interested in this problem? Broadly speaking, there are three reasons we look at multi-robot and generally multi-agent systems. The first one is that there are a number of high-priority science questions identified in the decadal survey that you cannot address with a monolithic measurement. You need to observe the same phenomenon from multiple angles, from multiple locations at the same time. For example, seismology. If you want to find out where seismic activity is coming from, having multiple seismometers with some baseline between them is really the best, if not the only way to get good localization. Weather and climate. My favorite example is studying the Martian atmosphere with a single weather station is the same as studying the Earth's atmosphere with a single probe in Milan. you can do a lot, but to get global insight, you need multiple measurements. And of course, in the astronomy and astrophysics domain, having distributed apertures, having multiple spacecraft working together allows you to have longer baselines and more light gathering capabilities than you can fit in a single launcher. The second reason to look at multiple robots working together is that some of the activities we perform most often, like exploration and mapping, are naturally distributed. By adding more robots, we just get things done faster. And the third reason is system-level resilience. The rovers we send to Mars today cost about $4 billion, and we have 200 people on Earth operating them. So if you do something that breaks the rover, you just lost $4 billion of taxpayer money, and the 200 of your friends are out of a job, which is not great. Now, if you have 10 robots performing science, you can be bolder. You can take higher risks to address high priority questions. And if you break a rover, it's still really bad, okay? But it's not the end of the mission. Now, so far, I have not talked about autonomy. Why do we need autonomy? Why can't we just joystick these robots? And the reason is really operational. If we had human operators work on multi-robot systems, the number of operators would scale somewhere between linearly and quadratically with the number of robots, because you need to look at not only at the individual agents, but also at how they interact. And that's not scalable. Whereas autonomy holds promise to take care of how the robots work with each other and allows the human operator to specify the high-level goal. This is what we want to observe, get it done. So today, I want to give you a glimpse, a brief glimpse, 1 minute each, at 3 projects I've been working on at JPL, and then do a deep dive into one. We'll talk about our work on understanding the science questions that require distributed instruments and generally multi-agent systems. Why go through the expense and complexity of having them? I'll briefly talk about our work for Earth science on sending swarms of probes under Antarctic glaciers to measure melting rates. I'll hint at what's been keeping me busy in the last 6 months or so, a tech demo to send 4 rovers to the moon, and then we'll do a deep dive into Mosaic. So let's get started. So I'm a technologist. I like to write code. I like to build things. But everything we do at NASA comes from science. Everything we do has to be justified because it will allow us to address science questions we otherwise couldn't. So we tried to compile a list of high priority science questions, and high priority means identified in the decadal surveys, that cannot be addressed with monolithic measurements. We got together 18 JPL scientists, held a number of workshops, and our work culminated in a white paper to the Planetary Science Decadal and a survey paper that we hope to submit next month to Planetary Science Journal. What we found is that there are at least 9 areas identified in the decadal just in planetary surface science, so no remote sensing, no astronomy and astrophysics. We really want these multiple measurements. And the top 4, in no particular order, are Martian climate and science. To understand the dust cycle, water cycle, CO2 cycle, you need multiple measurements. The source of methane plumes on Mars, we've seen methane on Mars. We don't know where it's coming from. And if it was on Earth, we suspect it will be a biosignature. So understanding if it's a geological phenomenon or something else is key. Seismology, as I discussed, and magnetometry, where having multiple magnetometers allows us to look at the time-varying response of the magnetic field and shed light on interior composition. Next, this is a really quick overview. I want to talk about ISSNAF because when people think about JPL, they typically think planetary exploration. But we also have a robust Earth science program, and ISSNAF is a great example. The goal of ISSNAF is to send multiple buoyancy-controlled vehicles that can go up and down underwater, but have no horizontal propulsion, and send them under ice shelves in Antarctica to measure how quickly these are melting and understand how climate change is going to affect sea levels. The thing is, to do that, you need to navigate for hundreds of kilometers under ice with no communication, in currents that you don't really know because nobody's been there before. And as I said, you can control your depth, but you're along for the ride horizontally. So we developed a guidance technique that we showed can guide these probes to the grounding zone where we want to go, And in simulation, holds promise to deliver about 30% more probes compared to state of the art. I'm going very quickly before the deep dive. So let's talk about Cadre. I wish I could tell you more about Cadre, but we're still in an early design phase and it's hard to get things clear. Here's what I can tell you. At JPL, as I said, we're all about doing science. We're about flying things. So all the research we do has to be motivated by science. How do we make sure that the technology we build will work? We test it. And Cadre will do just that. We plan to send 4 robots, fully autonomous, to the moon in 2024 and use them to perform exploration. The dream is that we push a button, we tell them, go explore, and after a few days, we get back a map with minimal human intervention, but of course, a lot of human supervision. We hope to fly in 2024. I am the planning, schedule, and execution lead for Cadre, and I really hope I'll be able to tell you more about this in an year or two. Now, after this whirlwind tour, let me dive deep into one project that I've been working on for the last few years, Mosaic. The idea behind Mosaic is simple. Imagine that you have a lander and a rover, and the lander has better batteries, larger solar panels, it doesn't have to drive, so it has more resources, more energy. But the rover is the one that can actually go places and do science. It would be natural to try and shift some of the boring activities, like localization and motion planning, to the lander, if the energy cost makes sense, so that you can free up resources on the rover and do more science. And that's simple enough, but what if you have multiple rovers that are contending for the lander's resources? Or what if you have multi-hop communication? So now talking to the lander requires you to bother your rover friends. Or what if there is no lander and the rovers have to contend with each other and trade resources with each other? This is the problem we're trying to solve. And as I walk you through the solution that we've been developing, I want to use this as an example of what is my philosophy in coordination of multi-robot systems. I think any successful solution to coordination of multi-robot system will share these 4 pillars. They have to be optimization-based. There are so many degrees of freedom in a multi-robot system. Who does what? When do they do it? When do they talk to each other? If you want to solve this, you really want the operator to specify what they want to do, and then figure out how to make it happen through numerical optimization. It has to be communication aware. We are really good at solving optimization problems, and I believe Bartolomeo is going to tell us all about it. I'm really looking forward to his presentation. But to get this working on our robots, we need to account for the fact that they're not a computer. They're multiple computers talking over radios, and radios aren't magic. Our solutions must be online. We have to solve them on our robots, which don't have great CPUs. And they have to be operable, because there is always an operator. And if the operator doesn't understand what's going on, these things are not going to fly, literally. So how do we do that? Let's start with optimization-based. We write down the problem of deciding who should do what and when as a mixed integer program. Don't worry about the maths. The message here is that we specify what we want to optimize. Maybe we want to maximize the science. Maybe we want to minimize energy usage or minimize the make span. We specify how the tasks depend on each other. You can't decide where to go if you don't know where you are. We specify the agent's resources and capabilities. The lander has better battery, has more energy, but only the rover can do science in situ. And we capture time-varying communication links. We capture the fact explicitly that agent can't talk all the time. And then we solve this through state-of-the-art numerical optimizers. We used Skip for those interested in ILP solvers. And we find a solution. So that's the first pillar. But this is not enough. This is a bird's eye view of the problem. But then we have to go and implement this on multiple robots that can't necessarily talk to each other all the time. So how do we distribute this problem? The approach we chose was a shared word approach. Intuitively, the robots gossip with each other. Every robot knows its own state. These are the things I want to do. This is where I am. This is how much communication bandwidth I have available. This is how much battery I have. The robots gossip with each other until they have a common picture of the system, until everybody knows what everybody else is up to. Then every robot solves the problem for the whole system as if they were the leader and executes its own part. And if the robots are on the same page, this results in implicit coordination. Now, what if the robots are not on the same page? We'll talk about that in a few slides. But here we've gone from a centralized problem to a distributed problem that we can solve on the multi-robot system. Now, if you know anything about mixed integer programs, they are expensive to solve. So to show that our approach works, we benchmarked it not only on my workstation, but also on a Snapdragon Flight, which is the processor we currently are using on Marseille, and my favorite on a PowerBook G3 that I got off eBay for $100, which has the same processor as our Mars rovers. This thing was built in 1999. And we showed that, first of all, we can solve these problems, even on the PowerBook. But more importantly, if you are okay stopping the solver early and taking a suboptimal solution, but making sure that you will get some solution in 10 seconds, you can solve problems with 8 to 9 agents on the PowerPC and 14 agents on the Snapdragon, which is enough for the foreseeable future, because we're not flying a huge system, at least for the next few years. Another thing we did to convince ourselves that this works online is we loaded up our software on 10 Raspberry Pis. We brought them at ICAPS 2019, and then we gave attendees QR codes where they could connect to a Wi-Fi network we built and just control them, add tasks, remove tasks, change the communication bandwidth between the system, between the nodes. And it's amazing how adversarial this testing can get, but we had a lot of fun and we passed flying colors. Now, the last pillar I want to talk about is operability. So we have a way of solving the problem in an optimization-based manner. We are solving this in a distributed fashion, where now we are solving n optimization problems, one per robot, and we are stopping the solver early. There are lots of moving parts, and it's really hard for an operator to keep track of everything. So we partnered with JPL designers to build user interfaces that would allow an operator to follow tasks as they move across the system and really understand what everybody's up to. I also mentioned that shared word works really well when the agents are on the same page, but when they are not, you can get really weird behavior where agent A thinks that agent B is going to do something, and agent B thinks that agent A is going to do something. And if you're looking at it from the outside, you see that the task didn't get done. Say nobody performed motion planning, and you don't know why. So we built a UX that would help operators spot this discrepancy in this n-squared problem, what every robot thinks about every other robot. We tested this through in-depth user studies with JPL operators who are used to working with robots, although single robots typically. And we passed with flying colors. We were able to show that the operators had good situational awareness of what happened, and we were able to debug. So these are the 4 pillars, but why are we doing this? Is it worth the extra complication of sharing tasks and sending computations around? Through extensive numerical simulations, we showed that depending on the case, you can save between 30 and 60% energy use and between 20 and 50% CPU, which to us makes it all worth it because these are extra resources that you can repurpose and use for science to get more done with the rovers that you have. And by the way, everything we've done is open source. So if you are interested, go to github.com/nasa/mosaic. And if you spot a bug, let me know, open an issue. Now, where do we go from here? It takes time to infuse ideas into flight. We've only been at this for a couple of years, so it will take more. But we are conducting mission studies. We're looking at how Mosaic can help a constellation of Mars CubeSats detect and react to dust devils, how it can help a constellation of balloons, well, a team of balloons on Venus react to volcanic eruptions. We are getting our code in shape so we can test it on the ISS, and the lessons learned are being infused in the cadre autonomy architecture. So that's it. We took a hard problem in multi-robot systems, and we came up with an optimization-based solution where we tell the system what we want to do and use numerical optimization. That is communication aware, that is, it works on a real system with real radios, is online, so we can solve it on real systems, and is operable, so operators can understand it. This is the end of my talk. Before we go to the Q&A, research is a team effort. everything I showed today, I was either the key technology person or the instigator for, but none of this would have been possible without my collaborators. So I want to acknowledge them and stop on this slide for any questions you may have.
Thank you very much, Dr. Rossi, for this very interesting presentation. We have several minutes for questions. So I would like to ask the first and then open the floor.
Please.
I would like to ask a question about the shared world architecture that you have been using as a very promising one. And I would like to ask you whether, how do you come up with this particular architecture, and what were the other candidates that were from which this was selected?
This is my favorite question in the world. Thank you so much. I'll try to keep the answer brief, but I may find it hard. We've been looking at this quite a bit. You can use a shared world architecture that works fairly well. You can elect a leader. So another approach to break the symmetry is for the agents to elect a leader. You use something like the Gallagher, Hamlet, and Spira algorithm, and then you converge cast the information to the leader. There are also explicit coordination approaches that typically go under the name of auctions in the literature, where the agents have a message board and they say, these are the tasks I want to do, and then they bid based on their resources. We actually spent a lot of time on these traits for Cadre. And the short answer is, in my view, and this is very opinionated, in a multi-robot system, you can't guarantee consensus. There are theorems about this, the general's problem you'll be familiar with. It's like chapter 1 of Nancy Lynch's book. So you have to choose. You can have a system that may sometimes stop if it doesn't agree. That's what leader election does. If the leader election goes wrong, or if you don't hear from the leader, you stop. That's what Paxos and Raft, which are used in the computer science literature, do. Or you can have a system that fails open, where you always have a solution on board, so you're always able to act, but you accept that there may be some lack of coordination. And it's an uncomfortable place to be, because you have to choose, which one makes sense. For this kind of R&D, we like to see how far we can push the system. So we are okay with the agents sometimes failing, well, sometimes acting in an uncoordinated way, so long as the operator understands it. Because typically things clear out. Intuitively, if two agents are assigned to the same task, whereas only one should be, they'll go there. Once they go there, they'll be in radio range and it will work out. I don't know if I should say this, but for Cadre, we are looking at a leader election architecture, because there we'd rather stop, since we are on the moon, and ask operators on the ground to check things out, as opposed to act in an uncoordinated manner. As for auction-based approaches, my discomfort with them is that they tend to require all-to-all communication, and they tend to require quite a bit of bandwidth. You have to tell everybody, hey, who wants to do this task? And then the agents have to come back and bid on it. And if you are communication constrained, that can be limiting. But these are the three areas that we look at. This was longer than I wanted. Does this address your question?
I believe so. Thank you very much. No,
Thank you.
I really believe
I
so.
love talking about this.
Any other questions from the jury members? If not, we open the floor to questions from the general public.
I'll also play this. So we built a software package that does the distributed word thing, and we presented it at ICRA. It's kind of cool too. So we siphon out tasks. So the agent thinks they're being done on board, but we decide where they should be done, and we dispatch them to another robot and then get back the reply. Again, go on GitHub and please explain more clearly. Sorry, questions?
So
I'm,
I have a question, actually. So if you had to explain to a 9-year-old kid what MILP formulation is in a sentence, how would you do that?
One sentence. You write down So I'm hesitating because I know Bartolomeo is going to explain that next, or I believe he is. I'm looking forward to his talk. But really, you have an optimization problem. Some of the variables are continuous. And if all the variables were continuous, this problem would be convex. So really easy to solve. As Steve Boyd teaches us, I like that we've all been influenced by him. But some of the variables are integers. They take integer values. And the nice thing about this is that you can represent discrete decisions. You can represent things like, do I do this task, or does this other agent do this task? Whereas with a convex problem, you can't do that. The convex answer may be you do robot A does 2/3 of it, and robot B does 1/3 of it. So, okay, the short answer is it's a formulation that allows us to write down what we want the system to do and capture discrete decisions, but at the same time is fairly efficient to solve in practice. If you are smart, I shouldn't say it's efficient, I know it's NP hard in the worst case, but it can be solved quickly with numerical trickery. I don't know, Bartolomeo, is it okay to call it numerical trickery?
I think it was a good answer, but I'm not in the committee. I really like the talk, by the way.
Thank you. No, I use integer linear programs. Did that answer your question, Professor Orlando?
Thank you. By the way, I didn't say that. That was a very interesting, and that's a very interesting topic, actually. Thank you. Congratulations.
Thank you
For your achievement.
So we thank again Dr. Rossi, and congratulations for your achievements. And we pass to the third presentation. Professor Bartolomeo Stellato. He's an assistant professor at Princeton University, and is presenting on data-driven algorithms for making optimal decisions in real time. Professor Stellato.
Okay, let me just move the screen. Can you all hear me?
Yes.
Yes.
Perfect. Okay, so let me start. So sorry, 1 second. There's the, let me see. So which video? I'm just using my slides as video, if that's okay for you, so that they'll copy the same thing. Is that okay? You see both my face and the slides?
Yes.
Okay, perfect. Okay, let's start. So thank you very much for having me here. It's actually a real honor to be between the finalists of the Strazzabosco Award and to be able to present my research to such an exciting community of Italian researchers in North America. And today I'd like to talk about decision-making for intelligent systems, which is the core of what I do. And I will tackle this problem or this line of research from a computational perspective. So I work a lot on numerical methods, and I work a lot on optimization. So these are the main tools that I will use to make systems make better decisions. So intelligent systems have changed a lot in the last years, and now they're able to really achieve and accomplish tasks that were unthinkable before. For example, lots of interesting applications that Federico mentioned are part of intelligent systems and new, some of the new capabilities, but also there's applications in autonomous rocket landing, where if you haven't seen this picture, this is the very popular application of company SpaceX that was able to autonomously land rockets on ships in the ocean, which was something that they were doing by applying complex decision-making routines. But also on the financial market, now we are investing on a daily basis, but also on a milliseconds basis or microsecond basis, so extremely fast over time, we're making trading decisions that are fully automated by intelligent systems. And this was all done manually before. So it was a huge transition in that field. And more on a common application for everyone, taxi driving apps now are what many people normally use to commute in major cities around the world. And these are some new capabilities that really are available because we are now able to make these decisions and reroute drivers and passengers in the best possible way. And if you want to see something more in the future, we are looking into companies and also academic institutions doing research in trying to make drones deliver packages or perform rescue missions or really do things that humans either cannot do for safety concerns or that we can that we are not able to do so often or so efficiently. So systems are becoming more intelligent, as we all know, but however, are they really as intelligent as we might think? So for example, this is a robotic system, and probably many of you have seen this video from Boston Dynamics where robots are now able to do parkour movements, which were quite impressive, I would say. However, the reality is that this does not happen in practice. In practice, they fail half of the time. And actually, this is what happens behind the scenes. And the reason is that all these movements are choreographies of movements that are applied in a sequence. And the robot is not really thinking about where it is. It's just applying these sequences blindly, or if you're more from control theory like me, they're applying these input actions in an open loop. So because there's no time to recompute the best decisions if the system goes in a different state, because these problems are too complicated to solve. So also in other applications that are more common in I would say in everyday life, self-driving cars like Tesla, you can see that there are lots of articles on newspapers where there really fatalities because they crash with pedestrians. That's a very well-known fact. And even in non-fatal situations, there's a situation, for example, this is a video of a testing of the Waymo cars, where if they can get usually stuck in intersections. And for example, in this case, they get stuck because they see two traffic cones and they're not able to replan correctly their trajectories because they've seen the situation is not what they've been dealing with before. And there's also even other situations where in San Francisco, people in a dead end of San Francisco would find lots of Waymo cars parked in their alley next to their house because they just get there and they don't know how to replan and efficiently get out of the street and reach their goal. So these systems are much more intelligent than before. However, there's some challenges that we are facing if we want to apply them and in a complex environments and make decisions that react and act in real time in the world. So what are these challenges that these systems are facing? If you want to make decisions in real time, you need to, first of all, apply them to specialized hardware, where, first of all, it's real-time hardware. Real-time does not mean necessarily fast, even though all these applications that I'm mentioning and that focused on are fast. Real-time is whatever happens in the world or on this system, you need to be able to compute decisions and do something at each time interval that is pre-specified. Also, there's limited resources. On these systems, we do not have large-scale clusters. They're just microcontrollers that run on embedded devices. So these methods need to really be customized for this kind of hardware. And also from the software point of view, these algorithms must be extremely reliable. So they need to converge, and we need to have a certificate that they converge in real time. Otherwise, we do not have safety guarantees, and systems can really not behave as expected. And lastly, these algorithms need to be able to learn from experience, because we are really facing lots of data influx in all sorts of applications. And traditional algorithms are designed in a way that they're just in a one-size-fits-all manner. But from a practical point of view, we really can exploit much more the experience and the data that we collect to make better decisions. So these are the challenges, and how are these systems actually applied in the world? How do we make these decisions? And usually we make decisions in real time by having a loop that looks like this, where we have an optimization routine where we compute decisions, and then the decisions are applied in the real world on a dynamical system or application that you consider, and then you can collect more data and make new decisions. So the beautiful thing about optimization is that we can abstract these decisions into a mathematical program, which is a abstraction of the decision-making process, where we usually we have some data that comes in, and from data, we want to make decisions based on the data that comes in. And we usually want to minimize a certain function, which could be, for example, if you're talking about a self-driving car, the objective could be to minimize the consumption or minimize the distance with respect to a target. And the constraints could be the dynamics of the system, so physics that needs to be respected, but also some locations of the obstacle where we cannot go, and also locations of pedestrians, and maybe also traffic rules in order to behave properly in traffic. So we really need to obey to these constraints and make actions accordingly. So these problems in general are extremely hard. In general, we cannot solve these problems, but we have specific classes of problems that we can solve. And also we have very similar problems in all of these applications, because everything that changes from time to time, since we're remaking decisions over time, everything that changes is that it's just that different data comes in. But for example, for a car, the physics does not change. The physics of the car is the same. It's just that maybe the information that we have about the location of the car changes. So in my research, I focus a lot on developing specialized algorithms that exploit the fact that we solve these problems in a sequence over time. And I'd like to discuss one of these algorithms that became very popular, which is turned into a software called OSQP. OSQP is optimization solver, so it solves a specific class of problems that are called quadratic programs, and it uses a new algorithm that is developed based on operator splitting methods, which are methods common in optimization. And we developed it with some pillars in mind in order to have it applicable in several different real life scenarios. So first of all, it needs to be efficient for sequential decision-making problems. So we really rewrote the low-level linear algebra to make it compatible and as efficient as possible for this class of problems. It needs to be robust, and for whatever data that we pass in, we made sure that nothing weird happens, like dividing by zero or a memory overflow, which if you have a safety critical application, it's really important that you don't want this to happen. Also, we made it embeddable. So embeddable means that it doesn't run only on your desktop. It can run from your toaster to a very large scale computing cluster. And in this way, we really allowed applications to go in various different directions. And we saw it applying in various different areas. But more importantly, we made it open source, and not only open source, but also extremely industry grade high quality and freely available. So I think that this is extremely important for us, especially for academics. We have the duty not only to distribute research and popularize it, but also for computational people like me, we need to make tools that are freely available and accessible to everyone. Also in the spirits of this award, that really, if we want to benefit society, we need tools that are easy to use, freely available, that everyone independently from the background can use. And since we developed this and we open sourced it and advertised it, we found so many companies and universities that ended up using this software. For example, Lyft, we discovered that is using it for designing incentives for drivers. So drivers, if you want to serve customers well in a large city, you need drivers to be redistributed in the right way. Otherwise, you can have areas of cities where you don't have drivers. So to do it, they design incentives. And to do so, they need to solve a very large-scale optimization problem where they need to assign how much all the incentives to give in different areas of cities. And this is exactly what they're been doing it. And we found out that from collaborations that were actually using OSQP, But also we found out that mathematical optimization is so flexible, and the beautiful thing is that it can be applied also to areas like particle accelerators. So next Oxford, this particle accelerator called Diamond Light Source that accelerate electrons and is used to design experiments where electron beams are thrown against materials and objects. So to do so, they need to guide the electron beam around this particle accelerator. And they did it by applying optimal control techniques where they use OSQP and they solve problem 10,000 times a second to redirect the beam in this particle accelerator. And they collaborated with us to put it on embedded linear algebra and linear algebra that is applied for that system. And also other tech companies like Google is using OSQP for robotic systems in simulations to really devise control algorithms with safety constraints. And there's many more applications that these companies are using. I would just to mention a few names also of universities that are using it. For example, in the US, MIT or Stanford, it's actually used as one of the main optimization solvers in the convex optimization class in Stanford and also at MIT and even at Berkeley and also in Europe in ETH Zurich and KU, and they're using this software. And I was pleased also to find out that people at Istituto Italiano di Tecnologia in Genoa, they're using it to control this famous humanoid robot called iCube. But this is not only applied in academia, also in industry, many people ended up using OSQP. There's not only the companies I mentioned, but even companies like Adobe for their multimedia products, and even large-scale hedge funds like BlackRock and Citadel, they use it to do backtesting simulation to experiments with their investment. So overall, we found out that just from the Python interface, we got something like 6 million downloads, which is a clear sign that the fact that it was open source, and companies explicitly told us the fact that it's open source and freely available allowed it to make an impact in society. And with industry, there's many more industries that we don't know whether they're using it because they don't come and tell us. But I think it's very exciting to be able to make decision-making tools that apply to all these fields. So I would like to mention, though, that this is not the end of the story. So this is one software that was particularly successful, but it does not exploit data or learn from data or improve from data. So in my research, I'm actually applying machine learning or data-driven techniques to improve optimization algorithms to make better decisions. And I work a lot on various different parts related to this. One is accelerating computations. Because if we want to solve these problems in real time, we need to really have algorithms that work fast enough in some situations. And I worked with collaborators, for example, at Berkeley on accelerating algorithms with my students here at Princeton on deriving complexity certificates so that we're sure that the algorithms run for any different application. And also worked with collaborators at MIT or even also Marco Pavone's group at Stanford or other collaborators here at Princeton on learning problems, whether when you have a decision-making problem, you just learn a simpler one that you can solve more efficiently that approximates the more complicated one. But this is not the only area. I'm also working a lot in decision-making under uncertainty. Lots of decisions that we make are in an uncertain world. So we need to be able to make decisions that really take into account the fact that the world is uncertain. So I worked also with collaborators at Stanford on learning control policies for stochastic control balances, and also making robust decisions with my students, Irina Wang, Cole Becker here at Princeton on robust decision-making by taking into account why the fact that the problems that we are solving are applied to uncertain systems. But to bridge this to practice and make really a change in the real world, we're looking into automatic code generation tools to apply these algorithms on embedded systems and really make people use them on whatever application they're considering. And this is also work that I've been doing with collaborators at Manchester, a software engineer here at Princeton, ETH Zurich, and also other works that are coming up in terms of automatic code generation. I think they're really the key to make these algorithms work well or be used. So just to give you a glimpse of why we're using learning, so this is, and why this accelerates, this is a decision-making problem of planning through obstacles. This problem is combinatorial because we need to really plan the trajectory of this robotic system through obstacles, and there's a combinatorial number of possible decisions that you can make over the horizon. State-of-the-art tools like Roby take something like 100 seconds to solve it. So if we need to replan or an obstacle comes in front of us immediately while we're letting the system run real life, we will not have the time to react fast enough. However, using these learning techniques, we were able to speed up these algorithms about 1,000 times compared to what state-of-the-art tools make, and be able to solve these problems in around tens of milliseconds for realistic systems. And this is really what changes between something that is theoretically possible to something that we can apply in practice. And this is done with collaborators at MIT and also at Stanford. So with that, I'd like to conclude and mention in my research, I really focus on building the next generation decision-making algorithms, which are optimization algorithms that we learn and adapt from data. And the goal is that they will be much faster than traditional methods. They will be reliable with certifiable complexity guarantees, and they will be embeddable. So after you learn, you could deploy them on whatever platform that could be either your toaster or a large-scale computing device, but they can go wherever you need. And to conclude, I'd like to thank all the collaborators and all the people I mentioned in this talk, and also the people that I didn't manage to mention that worked with me along the way. I wouldn't be here without them. And I would also like to thank the organizers, and I'd be very happy to answer any question.
Thank you very much, Professor Strazzabosco, for a very, very interesting presentation. And I would like to open the floor for questions, first from the jury members.
I have a question. So you mentioned the paper in which you developed the operator split SQL. Can you describe a little bit more the algorithm? Because you presented today a lot of very interesting applications. Can you give us just a gist of it? Let's say, a 9-year-old is let's assume that I have some basic mathematical background. Okay, I'm not an expert in optimization, but can you describe what was the state of the art before and after that algorithm was invented?
So yeah, the state-of-the-art before these operator splitting algorithms are algorithms that have been available for a while. They gain lots of popularities nowadays because they're basically a divide and conquer technique. So you have a complicated problem or a problem that you cannot solve all together, and you just split it in easier components. And for example, for quadratic programs, usually you have a quadratic objective function that is convex and linear constraints. And with the algorithm that we developed, we rewrote the steps by splitting the objective and the constraints in a smart way, so that it usually boils down to a sequence of operations that are a linear system solution that is the bottleneck of many numerical algorithms, I would say. And this linear system has nice properties. I know you're more into numerical methods, so I'll be happy really to talk even more about that, but the linear system is always solvable independently from the noise that you have in the data. So you don't have weird things happening. And also this linear system can be pre-factored, which means that to solve linear system, usually you have some techniques where you do one step, and this is called pre-factoring, and then you solve it afterwards. This pre-factoring routine is a costly operation, but since you make decisions over time, can be amortized, and you can reuse the same factorization across different decision-making problems. Okay, so I would say we applied.
If I understand it correctly, the splitting allows you to pay a check at the very beginning, and then you can basically use these splitting operators down the road because they don't change in the composition that you made of the programming problem.
Yes, I mean, there's way more benefits. We also developed some invisibility detection techniques. That was a new theoretical results where you could understand if the problem is invisible, which is extremely important if you have control problems. This was not known This was not known, and first order methods are not very good at detecting invisibility. Also, we exploited the fact that compared to other algorithms, now I don't want to dive too much in the math, but for example, interior point algorithms became popular in the 90s and early 2000s. They cannot be warm started. So this means that if you solve a sequence of problems, the fact that you made a good decision at the previous time instant cannot be exploited to accelerate the algorithm further, while first order methods can enjoy these properties. And also there's other techniques that we applied in the algorithms. I didn't want to dive too much into the math on.
It's always a difficult choice. It's always a difficult choice in a presentation like this one, you know.
So yeah, because I think it tends to be technical, very easy, but I would say we also exploited the linear algebra in the sense that, as I said, it could go on embedded platforms, and we also exploit the fact that we do not perform dynamic memory allocation after you do this pre-processing step, which is also dangerous if you have real-time systems, because your memory could not be enough to allocate more.
That's right.
And on a safety critical device, you never want to do that. And then we also applied it to GPUs, for example. There's not many solvers that run on GPUs, which are very common hardware nowadays. And by adjusting the linear algebra in this solver, we were able to, users can just apply it on an embedded platform or a multi-core CPU platform, or also GPUs. So we kept simplicity, but also flexibility in mind. And this is also what I do in all the other projects, I would say, that I'm focusing on also with my students.
Thank you. Thank you for your answer, and congratulations.
Thank you.
Thank you. And there is no time, unfortunately, for further questions, but I would like to thank you, Professor Stellato, and all of our presenters today, and congratulate with you for your achievements, and wishing good luck for your future. And a few closing remarks. I would like to thank as well the Strazzabosco family for the support, and all of the candidates that applied to the 2021 Strazzabosco Award, the jury members, Professor Elena Orlando, Professor Guglielmo Scovazzi, and I would like to acknowledge the administrative support of ISSNAF, in particular of Enrica De Torre, ISSNAF Vice President, and of Carlotta Borromeo Kendall. And in closing, I would like to remind that the winners, the winner of the Strazzabosco Award as well, will be announced at the ISSNAF annual event. We will be held on December 9 at 9 a.m. Pacific Standard Time, in partnership with the Embassy of Italy in the USA. So save the date for that. And with this, I close this symposium of the 2021 Strazzabosco Award. Thank you very much.
Thank you.
Thank you.
Thank you very much.
Thank you.